and welcome to the Global Agriculture Innovation Forum. I'm Gerald Shively, Associate Dean and Director of International Programs in the College of Agriculture at Purdue University, your host for this event. I'd like to welcome you on behalf of the organizing committee, our advisory group, and everyone contributing to this effort. I'd also like to thank USDA, especially the Foreign Agricultural Service, for its continued support of forum events. The goal of our year-long series of events is to explore the frontier of agricultural innovation with a view to feeding the world sustainably. With today's event, we launched the second theme of the forum, genetic improvements in smallholder agriculture. Previous sessions in this series included presentations and moderated discussions with more than 20 global thought leaders on the topic of farms and farmers of the future. Those recorded presentations are now archived and available on the forum website. The website also includes links to a range of curated resources related to session topics. Without further delay, let's get started with today's outstanding set of thought-provoking presentations on agricultural innovations. I'd now like to hand it over to our moderator, Dr. Susan McCooch, who joins us from Cornell University, where she is professor of plant biology, plant breeding, and genetics. Please enjoy the program, and please stay for the live question and answer session that will follow the presentations.
Thank you, Professor Shively, for the kind introduction, and to Purdue University for organizing this panel as part of the Global Agriculture Forum. I'm Susan McCooch. I'm a professor of plant breeding and the director of the Cornell Institute for Digital Agriculture. I will moderate today's panel on genetic innovations in crops. Breeding and selection of improved crop varieties traces its origins back to our Neolithic ancestors, who began selecting for desirable traits in wild populations growing in their environment. The combination of natural and human selection led to the development of domesticated plant populations that were simultaneously well adapted to their environments locally, and they helped to satisfy human need, paving the way for human settlements and civilization as we know it. Interestingly, plant domestication happened in many different parts of the world at roughly the same time, between 8,000 to 10,000 years ago, a period often referred to as the Neolithic Revolution. But what motivated this new form of behavior, and why then? Part of the answer appears to lie in the fact that the Earth experienced a period of significant climate change about 10,000 to 12,000 years ago, as it emerged from the Ice Age. With warming temperatures, rising sea levels, plant and animal populations expanded their ranges and diversity, and early human populations responded to these changes by foraging the most desirable fruits, nuts, and seeds from wild plant populations and propagating them, often unconsciously, as progenitors of subsequent generations. This cycle mimicked the forces of natural selection and slowly but dramatically shifted the genetics of populations across the landscape, favoring plant traits and characteristics desired by humans. Today, human survival depends on the productivity of crops first domesticated during the Neolithic Revolution, and survival of those crops is equally dependent on humans. As we face a new era of climate change, plant breeders are being asked to address many compelling challenges related to the sustainability of agriculture. There is urgency to develop new crop varieties that can respond to increasing climate variation, characterized by complex combinations of heat, cold, drought, flooding, rapidly evolving populations of pests and pathogens, and constraints on agriculture's use of natural resources, while also addressing consumers' demand for enhanced nutritional quality and livelihood security. I think you will enjoy the diverse perspectives of the four presenters in this panel, and it is now my great pleasure to introduce Howarth Boy, founding director of Harvest Plus. Howdy received the World Food Prize in 2016 for pioneering the concept of biofortification in the early 90s and founded Harvest Plus in 2003. He has devoted his career to turning his idea into a global movement that currently reaches more than 50 million people in smallholder farming families in low-income countries. He continues to actively champion biofortification and the work of Harvest Plus and the international agriculture and nutrition communities. In 2018, Boy was named a nutrition champion by the African Leaders for Nutrition, a joint initiative of the African Development Bank and the Africa Union to promote high-level engagement and advance the nutrition agenda. Howdy.
10 minutes is not much time to cover what I've been working on for the past 25 years. I will spend 1 minute each to highlight 10 key aspects listed on this slide related to realizing the innovation of biofortification. Biofortification is the process of breeding for higher levels of minerals and vitamins in staple food crops, then scaling uptake by farmers and consumers to reduce malnutrition in lower and middle income countries. Biofortification has a public health objective and so must be funded initially in the public domain, then later involving the private sector to secure uptake and sustainability. This picture shows a deep orange maize developed through conventional plant breeding, which is high in vitamin A. Africans eat white maize, which has no vitamin A, but vitamin A deficiency is widespread. The orange mazes are high yielding and sell for the same price as white maize. Getting Africans to substitute orange maize for white maize in their diets will go a long way toward eliminating vitamin A deficiency at no extra cost to consumers. 2 billion women and children are at risk for vitamin A, iron, and zinc deficiencies. These deficiencies impair cognitive development and are the cause of elevated levels of sickness and death. It is necessary first to convince people that your new idea has the potential to be more cost-effective than current interventions. Vitamin A supplements given to preschool children once every 6 months have saved millions of lives. 10 billion vitamin A supplements have been given out over the past 20 years at a cost of $1 to $2 per supplement. Do we keep giving supplements over the next 20 years? A comparative advantage of biofortification is that recurrent costs are low once nutrient-dense varieties have been developed through agricultural research in a central location, then can be transferred for adaptation in country after country. This slide shows cost per disability adjusted life years saved for a wide range of interventions. The dark green and light green lines are for biofortification, which predominate at the left-hand side of the diagram where costs are lowest. Orange maize varieties must be high-yielding and profitable for farmers to adopt and produce them. Plant breeders were initially very skeptical. Their presumption was that there would be a trade-off: breed for higher nutrient density, and this would be associated with lower yields. Would there be a negative genetic linkage? Moreover, adding a new trait, human nutrition, as a breeding objective would slow down progress on realizing yield-increasing traits for the same level of investment in breeding. Long story short, there was not a negative genetic linkage. In fact, plant nutrition is improved by higher seed zinc content. Public funding for biofortification allowed for an increase in total funding for plant breeding. 340 biofortified crop varieties have been released globally. Biofortified crops are being grown by a minimum estimate of 10 million farm households. Nutritionists were skeptical that the higher levels of minerals and vitamins that could be bred into food staples would be enough to have a public health impact. Donors to Harvest Plus have funded 15 published efficacy trials. women and children consuming the biofortified varieties have shown improvement in mineral and vitamin status as compared with women and children eating the regular non-biofortified varieties. These studies have also demonstrated that functional outcomes are improved, such as less sickness and better cognitive and work performance. Once new biofortified varieties are released, typically only a small quantity of seed is available. In any given country, it is a huge effort to multiply seed, then make farmers aware that the new varieties are available. In the case of higher iron and zinc density, the simplest strategy is to piggyback on superior agronomic traits coming out of agricultural research institutions. The motivation is that farmers want the most profitable varieties possible. The iron and zinc cannot be seen or tasted. An analogy would be putting fluoride in water systems. In the case of vitamin A, consumers must be educated what the benefit is of the orange color, the vitamin A that will give better nutrition to the health of their families. It takes a wide range of partners working all along value chains to accomplish scale-up. This slide shows the partners that Harvest Plus works with in India in scaling up zinc wheat and iron pearl millet. No innovation can be achieved without funding. In the case of an agricultural project, and a plant breeding project at that, funding must be sustained over a minimum of 20 years. A difficulty is that donor interest tends to be cyclical. It is important to diversify the funding base as much as possible. It took 10 years to reach a minimum level of funding just to get started in 2003. As you can see in this slide, the idea was popular among donors in the first dozen years or so. Revenues increased year in and year out. Budgets peaked at somewhat above $40 million per year, then have declined. Expert communications and advocacy are essential ingredients to sustain interest both in scaling up and in continued funding. As successes occur, impacts must be measured as rigorously as possible, then communicated accurately as widely as possible. Plant breeders, human nutritionists, seed and extension experts, economists, and several other disciplines and fields have all worked together to make biofortification a success. We came up with a framework shown in the slide to meet and work together. Sometimes we organized ourselves by crop, putting persons from all areas of expertise together. At other times, we put the experts together from a single expertise who could compare and learn from successes and failures from working across several crops. It was important for everyone to have the same vision and to appreciate the role of each component in the overall matrix. Early successes along one column could sustain policymaker and donor interest for the entire program. Inevitably, there are disappointments and failures along the way. Once I had my big idea described in the beginning, I had to determine whether it was actually scientifically feasible. I first consulted the plant scientists. I visited the 9 CGIAR centers highlighted in yellow in this slide in 1993 to seek their opinions and interest in working on micronutrient deficiencies. Although there were a few takers, overwhelmingly I was told that my big idea was a non-starter. It is tough deciding when you have reached the point of having to give up on your innovation, but hang on as long as you can. In 2012, when we were nearly 10 years into implementing Harvest Plus, the head of communications convinced me to engage our management team in an exercise to define what I will call our institutional culture. we hired a firm to run and coordinate the process. This slide shows what we called the brand promise, the brand personality, brand values. Bridging the Delta is the interdisciplinary communication. Show don't tell was the need for rigorous scientific evidence. Tenacity, learn by taking risks, are self-explanatory as our game changer and creative disruption. I loved it. There was much consensus that these were values that we all had. The idea had been to use this and other related tools to help manage Harvest Plus. However, this was all much too touchy-feely for some. Being so divisive, it never really took off as a management tool. But I think the fact that we had implicitly already held these institutional values broadly was quite important to the success of Harvest Plus. More recently, I have been reflecting on what agricultural scientists of future generations will be able to accomplish with new tools, some yet undiscovered. One of the limitations of biofortification using conventional breeding has been adding single nutrients to crops. Second nutrients are added sequentially, not simultaneously. Moreover, climate change is putting new demands on plant breeders. I realize now that for biofortification to reach its full potential, it must be relatively easy and rapid to transfer multiple new traits to new varieties. My hope is that as these more powerful techniques become available and practical to use, that agricultural scientists will be even more focused than now on adding nutritional characteristics. How can I reach into the future and speak to agricultural scientists? In closing, let me read this quote. Such intimately related subjects as agriculture, food, nutrition, and health have become split up into innumerable, rigid, and self-contained little units, each in the hands of some group of specialists. The experts soon find themselves learning more and more about less and less. The remedy is to look at the whole field covered by crop production, animal husbandry, food, nutrition, and health as one related subject, and to realize that the birthright of every crop, every animal, and every human being is health. This quote sounds very contemporary, but it was written in 1945. These ideas and concepts, broadly speaking, have been around a long time, but it takes leadership and perseverance to put them into practice.
Thank you for that lovely and interesting presentation, Hadi. And now I'm going to introduce our next speaker. But before I do, I'd just let everybody know that we're encouraging you to enter any questions you have in the Q&A window. And you can do that at any time along the way. We will be gathering the questions and sharing them with the audience at the end when we have our whole panel ready to go. Elcio Guimaraes is the Director General of Embrapa Rice and Beans Center. He's had a long involvement with Embrapa, where he currently serves as the Director General. He spent many years in the field as an upland rice breeder, which is where I first knew him, focusing on the challenges associated with weed competition in areas where rice is cultivated without standing water. He also spent several years as a rice breeder at the International Center for Tropical Agriculture, known as CIAT in Colombia, before taking a position with the Food and Agriculture Organizations of the United Nations, the FAO, in Rome, where his major task was preparation of the second report of the state of the world's plant genetic resources for food and agriculture. Without further ado, I will introduce Elcio.
Hello, I'm Elcio Perpetuo Guimaraes, Director General of Embrapa Rice and Bean Research Center, located in the Brazilian Cerrado. I will focus my talk today on two main points. First, when breeding for productivity increase, make sure cropping systems are a part of your equation. And secondly, efficient breeding tools are key to positive results. Let's start by saying that genetic innovations in breeding plants for high productivity are not going to solve the world's food demand in the coming decades. However, I have no doubts that it will guarantee that crops have enhanced the capacity to deliver high productivities in the right environment. Looking at the crops, as you can see in the slide, we can split them in two groups. The big ones, rice, maize, wheat, soybean, cotton, sugarcane, and the other ones, where roots and tubers, pulse, vegetables are. In general, for the first group, breeding innovations are pushed by the private sector, which has been investing a large amount of money to develop improved cultivars with enhanced productivity. In this context, it's worth mentioning the role CGIAR played on rice, maize, and wheat breeding. For the other group, breeding efforts have been made based on resources coming from the public sector, which in general suffers from changes in the economic situation, policies, and so on. What makes continuity and long-term planning quite challenging. I don't see the situation changing significantly in the coming years. Most of the breeding efforts to increase productivity focus on increments per unit area. However, looking forward in solving the world's demand for food and considering how farmers manage their properties, more attention should be paid to increase productivity for the whole cropping system. In this regard, it's also highly relevant to consider productivity per unit of time, per unit of input, and relevance to the amount of emissions produced. Today, farmers are opening up markets based on green production. Just 2 weeks ago, when I was preparing for this conversation, a farmer came to visit us here at Embrapa, and he cultivates about 1,100 hectares in the Brazilian Cerrado with soybean, maize, and common beans. His question to us was, how can I get more grains and return for my resource in the 365 days I'm cropping my farm? He was not focusing on high-yielding soybean, maize, or common beans. He was asking about high-yielding and profitable cropping system. This is the direction I see agriculture moving forward regarding yield increase. Answering to questions like that, breeding programs are producing innovations focusing on yield increase per unit of time and or per unit of input. For example, here at Embrapa, one of our breeding focus is to respond to demands of cropping systems where maize and soybean are the main crops. To be able to include common bean in the cropping systems, we had to develop a super early cultivar with 65 days from sowing to harvesting, which was never done before. As you can see in the slide, it yields 45 kilograms per hectare per day, about 3 tons. Modern cultivars can yield 4 tons. The biggest advantage of the super early is to fit in the current cropping systems where soybean and maize are the main crop. So my first message is, in the coming years, genetic innovations have to be considered the whole cropping system and not one crop in isolation. Therefore, productivity increase will come from increase per unit of area, time, and input. Early maturing and input-efficient cultivars become priorities when breeding for productivity increase. Well, let's move to my second point, the breeding tools. It's not possible to talk about genetic innovations without mentioning the tremendous progress made in the development of the new breeding techniques and how they have been used to strengthen breeding for productivity. Today, we can look at traits difficult to breed for as the ones mostly affected by climate change, like drought, flooding, heat, and cold, and use molecular tools to tackle them. Similarly, the breeding programs are enhancing productivity through breeding for pest and disease resistance, using molecular tools that goes from simple markers to edit genes. An example of genetic innovation combining molecular tools and classic plant breeding is the exploitation of our gene banks. Here is a story of success where crop wild relatives were used to improve productivity in pigeon pea. To achieve it, breeders used the combination of molecular tools to determine the genetic diversity and to follow the line development process, basically the backcross, to produce crop wild relatives introgressed lines that yield better than the elite check, as can be seen in the figure. These improved lines are now in the advanced yield trials of national programs in India, Myanmar, and several countries in Africa. I want to highlight that this work was supported by the Global Trust, and it was done by Shivali Sharma at ICRISAT in India. In spite of recognizing the importance of the biotechnological tools, my next example of success focused on the use of recurrent selection in breeding populations to increase yields in rice. The story is related to our rice breeding program here at Embrapa. The graphic, just you can see, shows that the genetic gains of Embrapa's rice breeding program in the last decade has been positive, and it's unquestionable. Looking at the Brazilian rice trend in productivity, the graph below, we can see productivity increase since the early 80s. And this is partly due to the gains, the genetic gains. I would like to talk a little bit more about the breeding tools. Today, in general, breeding programs must use molecular tools to increase efficiency. And you'll see and you'll hear more about it in the coming talks. Going back to our two groups, in the big ones, modern biotechnological tools must be the way forward, as their yield potential is already high, and yields increments are quite difficult to be achieved using only conventional strategy and tools. However, for the crops bred by the public sector, molecular tools must be put in the right context and used when necessary. I have seen many national programs with top-of-the-line equipment sitting in their labs where electricity and water quality were the limiting factors. In addition, equipment are expensive and become obsolete quite quickly. I'm bringing these issues here because this seminar is seen all over the world, and breeding capacity varies tremendously among countries. They do not only vary, but according to data we generated at FAO in 2006, the world's breeding capacity is not increasing. Contrary, it's decreasing in many countries, as you can see in the graph. I believe the situation has not changed significantly. Therefore, focus and the right tools are key for success. Continuing looking at breeding capacity to deliver innovations, I want to mention that in January 2020, I visited CGIAR centers ICARDA in Morocco, ICRISAT in India, CIET in Colombia, and CIP in Peru. During the visit, everyone stressed the significant decrease on their institutional breeding capacity. If we look at here, where we are at Embrapa, our rice and beans breeding capacity today is the same as it was 15 years ago. Again, If we want to be successful in bringing to the agricultural sector innovations through breeding, focus and the right tools are key. My second message is don't get carried away by the tools, mainly the new ones, but make sure you understand how useful they are for your breeding goals. Breeding for productivity increase is a tough job and requires a lot of field work and sunshine on your head, in addition to efficient tools. Summarizing, in the coming years, breeding for high productivity must focus on breeding high-yielding crops in the context of sustainable cropping system using proven tools. Thank you very much.
Thank you very much, Elcio. I think we'll all walk away with a memory of your concepts on tools, focus, and strategy as being key to success. And now I'd like to introduce Pamela Ronald. Pam Ronald is a distinguished professor in the Department of Plant Pathology at the University of California, Davis, and with the UC Davis Genome Center. She's well known for major discoveries in plant molecular genetics, focusing on disease resistance and submergence tolerance in rice, which you'll hear more about today. And she's a recently elected member of the National Academy of Sciences in the United States. She was a 2020 World Agriculture Prize laureate and was the first woman whose work was recognized by the Global Federation of Higher Education Associations for Agricultural and Life Sciences. She also serves as the director of the Institute for Food and Agricultural Literacy at UC Davis. Pam?
Hello, I'm Pam Ronald. Thanks for joining us today. Today, I'll describe how genetic improvement can enhance climate resilience of crops. As we know, if the food system is to withstand climate change and sustain a growing population, it must become more resilient and efficient. Climate change adds many new challenges for farmers. Consider flooding. Rice grows well in standing water, but most rice varieties will die if they're submerged for more than 3 days. Now, this is an image of kids walking through their family rice field in Bangladesh following a flood. This family will not be able to harvest rice from the center of this field. As the climate changes, the Intergovernmental Panel on Climate Change predicts that floods will increase in duration and intensity. 25% of the world's rice is grown in flood-prone areas. In South and Southeast Asia, 4 million tons of rice, enough to feed 30 million people, is lost every year to flooding. Now, this region is home to 70 million rice farmers, many who live on less than $3 a day. Rice breeders have long known about a variety of Indian rice that can tolerate submergence. In the 1980s, breeders used a conventional breeding approach to introduce this flood-tolerant trait into rice varieties. However, the resulting rice varieties were rejected by rice farmers because the breeding dragged in undesirable traits such as lower yield. At that time, breeders did not have a way to introduce the trait more precisely. About 25 years ago, my colleagues David McKill and Kenong Xu mapped this important trait called submergence tolerance 1, or SUB1. In 1995, we began a collaboration to isolate the gene encoding the SUB1 trait. We were able to successfully isolate the gene encoding the submergence trait using a map-based cloning approach. On the left is a conventional rice variety that was grown for 2 weeks, submerged for 2 weeks, and then allowed to recover for 2 weeks. On the right is a rice plant that we genetically engineered in my lab with the new rice gene we named SUB1A. You can see that the genetically engineered rice survived the flood. We were amazed and excited that the effects of this single gene were so clear. At this point, we were certain that we had identified the gene that made the plant tolerant of flooding, but what was the mechanism of action and would it work in the field? Over the years, a talented group of researchers have begun to uncover the mechanism with which sub-1 locus enables plants to endure complete submergence for prolonged periods. Submergence creates a low oxygen environment and the accumulation of ethylene. In the absence of sub-1A, plant elongation signaling pathways mediated by the plant hormone gibberellic acid causes plants to grow rapidly, which depletes their carbohydrate reserves and die. In the presence of sub-1A, ethylene activates sub-1A transcription. We also found that sub-1A activates expression of the ethylene response transcription factors ERF66 and ERF67. Dr. Shi's team showed that a low oxygen environment stabilized the ethylene response transcription factors, which are direct transcriptional targets of sub-1A and are upregulated by sub-1A. These transcription factors directly or indirectly activate expression of submergence responsive genes. Professor Bailey-Serre's team showed that sub-1A also downregulates carbohydrate metabolism and induces ethanolic fermentation. Sub-1A also downregulates gibberellic acid signaling, and the resulting reduction in cell elongation and carbohydrate breakdown conserves the shoot meristem and energy reserves until the flood subsides. Together, these traits contribute to submergence tolerance. So does this trait work in the field? The answer is yes. Please watch this 4-month time-lapse video. It shows the sub-1 variety developed at the International Rice Research Institute using marker-assisted breeding. On the left is the rice variety with the sub-1 gene. On the right is the conventional variety. At the beginning, both grow normally. However, after the field is flooded for 17 days, the conventional variety does not thrive. In contrast, you can see that the sub-1 variety recovers rapidly from the flood. In these experiments, the sub-1 variety produced 3-fold more grain than the conventional variety. I love this video because it shows the power of plant genetics. In 2008, our team visited farmers in India and Bangladesh who had planted the new variety called Swarna sub-1. This image shows the fields after a naturally occurring flood. You can see that the Swarna sub-1 variety grows very well. It had a 60% yield advantage compared with the conventional variety called Swarna. In 2017, more than 6 million farmers grew sub-1 rice. An important question for sustainable agriculture is who benefits from technological innovation. And Kyle Emmerich and researchers at Tufts University and UC Berkeley carried out a field experiment to address these questions. They looked at a region in eastern India, as shown on the lower right of the map. And this region is blown up here. In red are high elevation areas, and in yellow are lower elevation areas heavily occupied by people belonging to minority social groups. The researchers randomly divided 128 villages in the state of Odisha into 2 groups, a treatment group where farmers were provided with Swarna sub-1 seed, and a control group where farmers continued to grow their chosen varieties, which is usually Swarna. This investigation confirmed early results that Swarna sub-1 delivers yield advantages to farmers during flooding and does not affect yield under flood conditions. These results show that flood-tolerant rice can deliver high yields, disproportionately benefiting the most marginal group of farmers. I hope this example gives you a sense that it is an exciting time for plant biology and agriculture. I am confident the global agricultural community will continue to make important innovations in plant genetics and breeding that will enhance the resilience of our agricultural system. I'm very grateful for the support of my laboratory team and my collaborators around the world, only some who I was able to list here. Thank you very much.
Thanks, Pam. It was an interesting version of how we sometimes learn from the past and resuscitate or bring back variation that farmers have known about for years, but now in a new context. And it was great work. So it's my pleasure now to introduce Mitch Tuinstra. Dr. Mitch Tuinstra is the Wickersham Chair of Excellence in Agricultural Research and Professor of Plant Breeding and Genetics in the Department of Agronomy at Purdue University. His research focuses on identifying genes and genetic resources that contribute to improved crop performance in stressful environments. This work is done in collaboration with scientists and breeders in North America, Africa, and Asia. The Heat Tolerant Maize for Asia project is a global development alliance to increase our understanding of heat stress tolerance in maize, and includes partners including CIMMYT, Purdue University, and Pioneer Hybrid, as well as partners in the National Agricultural Research Systems and seed companies from South Asia through the support of USAID. Mitch?
Thank you very much, Susan. I really appreciate the chance to have a few minutes to share with you this morning my thoughts about crop production and under conditions of climate change, and a chance to talk about climate resilience in maize. Today I'll be speaking with you about genetic innovations to enhance resilience of maize under abiotic stresses. To start this presentation, I just wanted to sort of reiterate the grand challenge of agriculture, and that's that we need to double global food, feed, fiber, and fuel production on existing farmland within the 21st century under conditions of climate change, while enhancing our soil, water, and air quality, biodiversity, and ecosystem health, and doing that in an economically viable and socially responsible way. A major challenge. We just heard a really nice presentation by Dr. Ronald about climate rice, and you can see based on her presentation, plant breeders are making really tremendous gains and improving crop tolerance to environmental stresses. Moving forward, one of the major challenges that we have is that environmental stresses rarely occur in isolation, so tolerance traits must be stacked to maximize crop productivity. So I'll be talking to you about stacking climate resilient traits in maize. There's a major challenge with stacking climate resilient traits in any crop, and that's that abiotic stresses are complex, and there are very strong interactions among tolerance traits and over environments. This is a table that I summarized from a paper by Dr. Cairns in Crop Science and in 2013. And what it shows is the relationships amongst these various tolerance traits. And it shows the genetic correlations for grain yield under drought, combined drought and heat, and under heat, and under well-watered conditions. And so, for example, if you look at the column for drought and you look down, what that indicates is if you select under drought, how does performance under drought compare with performance under combined heat and drought stress, or performance under heat, or performance under well-watered conditions? What's the relationship between performance under those various environmental conditions? And what you'll see is that these are surprisingly low values. That performance under drought is really not predictive of what you would see under performance under drought plus heat stress. Or if you look at the fourth row of this table and you look at performance under heat stress versus performance under heat plus drought, and you'll see that the genetic correlation is actually negative. And so when you start stacking these climate resiliency traits together, we oftentimes see some unexpected results, and it's important to actually address these things directly because they indicate complex interactions. So today I'm going to be talking about genetic innovations as it relates to climate adaptation. And I'm going to be talking first about traditional crop improvement strategies using native genetic variation or genetic resources. And the first project that I want to talk about is a project called the Heat Tolerant Maize for Asia. The acronym is HTMA. This is a project that's being coordinated and run by CIMMYT. We're getting close to 10 years into the project. And it's a project that I think really does a nice job of highlighting the opportunities that we have to develop climate resilient crops. So when I talk about heat stress tolerance, what do I mean? And this happens to be in South Asia. So if you look at the map on the right, you'll see that much of the plateau that's in South Asia is represented by very high temperature conditions, greater than 35 degrees Celsius, during this summer season. And so this is roughly between March and June of the calendar year. And if you look on the left, you can actually see the max and min temperatures that would be expected during the spring season for maize production. And you'll see that the max temperatures are somewhere around 40 degrees or 105 degrees Fahrenheit. And the minimum temperatures are 23, 24, 25 degrees. So between somewhere in the mid 70s. So these are very warm environments that would be much warmer than what we would see in the United States in the Corn Belt. So the Heat Tolerant Maize for Asia project is a global development alliance supported by USAID that integrates the resources of both public and private sector partners to improve heat stress tolerance in maize. So again, this project's been running for nearly a decade. The very first hybrids developed and identified in this program were released in 2015. These hybrids exhibit very good performance under high temperature conditions during the spring season and during the main season, during the main growing season. And not only is performance excellent, the end use properties of these hybrids are also valued by the end users. So starting with this first release in 2015, we've seen additional hybrids released in subsequent years, as many as 14 in 2019, somewhat fewer in 2020 as a product of this COVID-19 challenges that we're still experiencing, but hopefully we'll be able to get back to releasing hybrids as we overcome the pandemic issues. And these are hybrids that are identified, developed, and released inside of the HTMA project. They're released to our partners, in many cases, our private sector partners, either regional partners or multinational partners that work in that region. And these are being produced then for maize farmers and oftentimes smallholder farmers across the region. What's particularly exciting about this project is that we're seeing increased production of certified seed. And so these are seeds being produced by the private sector, being made available, sold to farmers in South Asia. Moving forward, we're interested in trying to incorporate multiple environmental stress tolerance into these hybrids. So the future efforts are tolerance to multiple environmental stresses with high yields under optimal conditions. So high yields in all environments. The first challenge in addressing that program desire is really coming up with harmonized screening protocols. And this is something that I think Summit does extremely well. If you look at these three booklets here highlighted on the top right side of the slide, these are the phenotyping protocols for drought stress and for heat stress. They describe how do you manage these environments to create the conditions that allow for efficient testing, and what are the phenotypes that need to be evaluated to quantify variability in plant responses to either heat stress or drought stress. The other major factor that we're interested in this project is that we believe that there's more effort that's needed to integrate and leverage both the temperate and tropical gene pools in providing solutions to climate resiliency. Historically, the temperate pool is managed separately, or it's used. They're subdivided into the tropical pool and the temperate pool. There haven't been a lot of efforts to. There have been some notable successes in this area, but moving forward, we think that there's really going to be an important opportunity to integrate the best of the temperate, the best of the tropical gene pools, to come up with even better hybrids that contribute to this global adaptation and climate resiliency of maize. And not only will the hybrids, or we've already have some evidence that the hybrids perform extremely well, but critically important in this endeavor of hybrid seed production is that using some of this temperate germplasm really provides an opportunity to enhance parent line performance. And so these hybrids tend to be oftentimes can be very producible. It's easy to produce hybrid seed. So there are other examples of these types of partnerships in Africa and in Latin America, but I think this is really an excellent example of the type of public-private partnership that's possible. But our private partners, the private seed sector, has also been very active in this space of developing drought-tolerant maize hybrids using the native genetic variation. Private sector seed companies are using advanced breeding technology platforms to identify and stack these drought tolerance genes into elite hybrids, followed by extensive field testing of these hybrids to guarantee performance under climate limiting conditions. There are a lot of companies that are working in this space. I'm just going to give you a couple of examples. One example is the Optimum Aquamax hybrids from Corteva Agriscience that have been developed that combine key native traits for improved root systems and silk emergence to enhance yield under both limited and optimal water conditions. Another example would be the AgriSure Artesian hybrid brand from Syngenta that integrate multiple genes for season-long drought protection. If you want to know more about these private sector projects, I've got the links here on the bottom of the page. You can read about them on the company's technology pipeline pages. And again, I think that that's an excellent couple of examples from the private sector where focused effort on breeding for drought tolerance has proven to be an efficient way to develop these improved hybrids. Another way another technique that can be used to develop climate resiliency is to use genetic engineering. Drought tolerance is a key target for many genetic technology companies. However, I've already highlighted this challenge in this talk. Given the complexities of drought tolerance and heat tolerance, there have not been very many examples or very few technologies that have been developed and delivered that produce commercially valuable levels of crop resilience or crop drought tolerance. One example that has been very successful is from Bayer Crop Science. It's utilizing a unique transgene, a cold shock protein from Bacillus subtilis called CSPB that enhances hybrid performance under drought. And these products that have this transgene are being marketed as Drought Guard hybrids, and they help corn plants resist drought stress and minimize the risk of adverse weather conditions. And again, if you have an interest in this technology, you can go to the Bayer website, read about it at their technology pipeline page. So just a few closing thoughts. There are considerable opportunities that remain for identifying and deploying genes and alleles that sustainably enhance productivity of crops like corn in hot and dry environments. And continued adaptation of our important food crops will be crucial to ensuring global food security. Much of the data that I presented here today are things that are publicly available, and I've cited those during my presentation. But one thing I did want to highlight is the work of my colleagues on the Heat Tolerant Maize for Asia project. I wanted to acknowledge the support from the USAID Global Development Alliance. We've been working in Bangladesh, Bhutan, India, Nepal, Pakistan, and the US on this project. A couple of collaborators that really have played a critical role in today's presentation. Dr. Zaidi, PH Zaidi, in Hyderabad, India, is the project lead, and BM Prasanna is the global maize lead for CIMMYT, and they played a critical role in this project, the success of this project, as well as in my presentation today. I also wanted to highlight the work of some of my students and my collaborators here at Purdue. Alex Renaud, Ryan Gibson, and Brad Theta are students that have worked on the project, and my co-faculty members here at Purdue, Guri Johal, Melba Crawford, and Ayman Habib. And if you look at this list over here on the right, these are our program partners across the region. And I think there's 30 different institutions, both public and private sector, that are on this list. And a project like this just isn't possible without the partners that we have. And so I wanted to highlight all the hard work that all of them contribute to the success of this project.
Thanks to all our speakers. We're now opened up for questions and answers, and I will be moderating this. So we've taken quite a few of your questions that have come in through the Q&A. I'll start by asking a general question. This will be directed at anyone who wants to answer. And as you know, you can see that our panelists are here live answering your questions. So we're grateful to have them online today from many different parts of the world. So the question that has come in and has been reiterated by several people in the audience today is, despite the merits of climate change resilience and nutrient-dense crops, many neglected and underutilized species called NUS, neglected and underutilized species, are low in terms of productivity and have limited geographical adaptation. But in that case, pre-breeding and breeding programs for developing superior varieties of these types of crops will be necessary for attaining the desirable productivity and profitability that will be needed. So compared to the main crops that we've discussed mostly in our panel today, how can we convince donors to make significant investments on the genetic improvement of neglected and underutilized species to deliver these public goods to benefit countries, particularly in the least developed countries, for food and nutritional security? An important question, and each of you have sort of addressed it in your own ways, but you've clearly been able to take examples from your own research. Let me leave that open for somebody who wants to tackle it.
Howie, that follows in your lap, Howie.
Well, I think it's fundamentally, a question for the breeders to, how much do you need this genetic variation to do the breeding that you need to do? I'm trained as an economist, so I'm not. I don't know how important that genetic variation is to the work that the breeders do.
Vencio, you should pick it up because you did give us one example.
Yeah, I think for us here, it's a tough question because nobody really, in terms of donors, they don't really care very much about the neglected crops. So what we do is trying to work together with the people that have the neglected crops as priorities for them. Within Embrapa, for example, we have research centers that are specialized on neglected crops, and we fundraise with the partners. So by ourselves, if we try to sell one neglected crop to a donor, it's going to be quite difficult unless if they see a clear advantage on having that neglected crop being worked out. What we try to do is to prove that there are market opportunities for that crop, and that calls the attention of the donors. But other than that, it's really tough. And I agree with the question. It's not easy to answer that one.
Pam, you were going to say something.
Sure, it was a great question. I just want to mention that there are several scientists that are doing some very interesting experiments. So Zach Lippman has taken an orphan crop called ground cherry and has used CRISPR to alter its structure, so to change branching patterns. And the idea is that we could take crops that are perhaps adapted to environments and very valuable, but haven't been grown widely because they are not producing well and have limitations. So I think that's an exciting area of research, using CRISPR on these highly adapted crops to make them more productive. I believe Rod Wing has a project with some wild species of rice as well. So there are scientists that are beginning to tackle that, and I do agree it's very important.
And Mitch, you have some experience with these crops.
When people ask me what I do, I call myself a C4 cereals breeder because I work on corn and sorghum and millet. And the interesting thing about those three crops is they represent different degrees of commercialization. And so you've got the big monster in the room, corn. It gets a lot of attention and a lot of investment. And oftentimes sorghum and millet compete in very similar or parallel spaces for acreage. And usually there's a reason why they're competing at a disadvantage. And so I think one of the challenges for plant scientists, plant biologists looking forward is looking for opportunities with these minor crops where they can compete head to head with the major crops. I think that there are lots of examples in sorghum. So I've been talking about drought tolerance today. Sorghum is the camel species for cereals of adaptation to limited water inputs. But it has other issues that need to be overcome in terms of adding value so that it competes favorably with corn in some of these environments. And some of those other related issues are things that we need to address.
So
Susan,
let me, yes.
Just to piggyback on what Mitch just said, if you are able to call the attention of the donors for other things than the crop per se, like the Global Trust is doing, trying to emphasize the importance of use genetic diversity, you do get funds for neglected crops. And the example I gave, the pigeon pea, is one of them. So they're not funding the crop as such, but they're funding the strategy of breeding or using the gene banks as source of genes for whatever crop they are targeting. So innovation in terms of how you propose your work is also valid to get funds for neglected crops.
So that's a really important point, Elcio. I agree that I've seen that and I've been active in that area myself. I think the utilization of the diversity that is in farmers' fields in many, many cases already, and that are already in marketplaces, but have not received the attention of breeders. Generically, if we want to increase diversity in farmers' fields, we're going to increase it not only within the crops we already grow, but by diversifying the crop selections. So there's an opportunity, I think, for funders, and maybe you guys want to just comment once more, and maybe part of another sort of twist to this question is we've seen this conversation evolving. I think Mitch was describing it in his presentation about convergence of international centers like CIMMYT and IITA working together with the private sector. And Elcio, I know that you've been working within Embrapa, you work across public-private sectors. So I guess the question is, what lessons have you learned, any of you, about public-private partnerships, and do they function well? And is this maybe a way forward to try to leverage a different approach in terms of the diversification of crops in farmers' fields?
I could make a comment on that to begin.
Great.
When we first started developing orange mazes for Africa, Africans are used to eating white maize, and we wanted to get there are a lot of maize seed companies operating in Africa, and we wanted them to get involved with us. And they basically said, where's the profit? Africans don't eat orange. You're never going to get Africans to eat orange maize. We said, well, we're breeding this for a public health objective. And they said, okay, fine. If you can ever create demand, come back to us and we'll get involved with you. What we found was that it was the smaller companies that were willing to take risks. They said, okay, maybe this is going to happen. So let's get in on the ground floor, and we can maybe go from a smaller company to a medium-sized company. And what the larger companies, basically their strategy was, well, if this takes off, we'll just buy one of the smaller companies and we'll get into the business. So that was our experience. We want to get private seed companies involved. It was exactly the same story with hybrid pearl millets in India.
Anyone else? I mean, some of you have had experiences. Are you in agreement that the smaller companies are more willing, the smaller private companies are more willing and interested in taking risks? Or maybe in finding a new niche, a new market niche?
They're certainly more flexible in terms of being willing to adapt strategies that might give them a competitive advantage in the marketplace, something that might be give them some, maybe not exclusive, but if they take it up early enough, they can be relatively exclusive and be an earlier adopter in the marketplace. I think one of the other major challenges in terms of plant technology, especially when you get out of some of the really big major crops that have lots of private sector investment already, is that many of our crops are hybrids, and the seed systems that support those crops are complicated. And if one doesn't take into account seed systems, either in hybrid seed systems or in variety seed systems as well, your ability to deploy technology, especially some of these value-added traits. I think Howie was talking about the fact that some of these traits on the nutritional side you can't see, so the end user has to be confident that there's something there. And sometimes that only comes through having confidence in private sector partners to deliver seed products that are real and not counterfeit. And I think that's one of the major challenges for the seed sector and for plant biologists in this space.
I agree with Howard. The small companies are more open to risk. Just to give you an example, right now we are bringing together 10 seed common bean producers to fund our bean breeding program. And the main point was to show them the advantage they would have compared to the multinationals in terms of getting specific products for their needs. So how you pitch to them your product is also key for the success. But yes, the small companies are more open to work with us, mainly if you're talking about not the big crops or the underutilized crops.
So, I mean, this is going to build on that question about value and economics, I think. Biofortification has enormous public health benefits, and how do you've certainly shown that over the course of a dedicated career. So the question is, do markets value those benefits? Are consumers willing to pay for nutrient-dense crops? And how long does it take to make a return on that investment? Or what is the targeted return on that investment?
Well, the main strategy for iron and zinc, you can't see the iron, you can't see the zinc, you can't taste the iron, you can't taste the zinc. So when I first got hold of the idea of biofortification, I said, well, what if Erie and Simmet had put in high iron and high zinc back in the 1960s when they first developed the modern varieties? The farmers adopted them because they were profitable, because they were high yielding, and they spread all over South Asia. We wouldn't have an iron deficiency problem and a zinc deficiency problem if Erie and Simmet had done that work back in the 60s. It's like putting fluoride in the water system. The farmers aren't demanding it. It's just that the breeders put it in. And the extra cost to the breeding programs is much less than the public benefit to the better health that people have when they eat the biofortified varieties. Now, the difficulty is with vitamin A, you change the color. So you can't use a fluoride, quote unquote, fluoride in the water approach with the vitamin A. So you really have to get the consumers to say, I'm going to eat orange maize. I'm not going to eat white maize. And once that happens, then the private seed companies are going to start producing all orange maize. So how do we make that transition from people being used to eating white maize to people being used to eating orange maize? So that's where we're in now. We've developed the varieties, we've done the nutritional studies. Now we're trying to get people to switch. Carrots, the example that I use are carrots are the first biofortified crop that I know about. Carrots used to be purple, used to be white. And now people don't even know that, and they think a carrot should be orange. And carrots provide a very significant proportion of the vitamin A intake in the United States. And it's just people have gotten used to that color and eating carrots that are orange. They're not gonna go in the grocery store and start buying white carrots now.
All right, I think we've all experienced this question and the polemic around biofortification of major crops versus diversification of the diet. And I'm sure, Howie, that you're not really advocating that everyone should just eat biofortified crops, but rather, hopefully, we're moving towards a diversified diet in the process. Interesting question came in. So we've talked quite a bit about abiotic stress and not too much about the response on the biotic side, meaning pests and disease resistance. And one question is, if you biofortify a crop, does it cause any changes in the relationship or the interactions between the plant and the pathogen or the plant and the insect? I'd love for somebody to take that one on. Have we seen any shifts in plant metabolism that would mean that we have these kinds of pleiotropic interactions? And should we be on the lookout for them?
Yeah, I'm not the expert. but I'm not aware of any. Let's just put it that way. I'm not, the people, our collaborators in our program have not pointed that out to me at all. But I defer to the plant scientists on that one.
We developed common beans, biofortified common beans here, and there's nothing different in terms of reaction either to abiotic or biotic stress on this variety. So I don't see any change, at least with my limited experience.
Pam, have you seen anything?
That's a good question. I think we always have to be on the lookout for such interactions, and I have not noticed anything in my own research or colleagues' research, but maybe I should just point out that the International Rice Research Institute and other international programs always test their new varieties in the field, in farmers' fields, and ultimately that is going to be critical, right? Because you might not notice something in your field trials, but then when it's in the hands of farmers, they're the ones that are going to be able to provide that feedback. But I think in general, for the kinds of traits we're talking about, there's not a really scientific reason why you would alter resistance to pest or disease when you're doing biofortification. But of course, that has to always be looked at quite empirically.
Mitch?
Yeah, I had a sort of a little bit of a unique example. So sometimes, and this is not directly biofortification, it's actually removing anti-nutritional properties from crops. And I think that there are a number of examples. This is not adding positive nutrients. This is taking bad things away from cereals and other commodities. But there are clearly examples when you're removing molecules that have anti-nutritional effects from crops that can have negative effects. And oftentimes, there's one example that we're working with in sorghum, where sorghum produces cyanogenic glucosides. It's used as a forage crop, and we've identified mutations that knock out that pathway. And so you've reduced the risk for animal producers on the back end, because now they don't have to manage the crop for cyanogenic glucoside production. And it is possible to show that these crops are more susceptible to insects, because that's what the CGs are doing there. But the question comes back for the plant breeder, what's the value proposition? In this case, the value proposition is you're making a crop, you're reducing end user concerns and making it more usable to the producer by alleviating concerns around potential forage anti-nutritional characteristics. And I think that's a complicated question. It's hard. It's one we're just now beginning to think about with economists, to think about if you reduce insect resistance by taking away anti-nutritional qualities, how do you compare the values of both of those characteristics?
Yeah, I mean, these are interesting questions at the level of how the biochemistry of the plant, if it appeals to a human, does it also appeal to an insect? Similar kinds of, we have documented effects over time that we lose certain types of resistance when we remove bitter compounds, et cetera. So it's not out of the question. Anyway, I thought it was a very interesting perspective. Here's the elephant in the room. I'm going to ask it now because it may occupy the rest of the conversation. I didn't want to ask it earlier. Given the issues around market acceptance of genetically engineered crops in some markets, should future innovations focus on conventional breeding rather than genetic engineering? And what tools should be employed? If you guys want to pitch on this one, is gene editing genetic engineering or not? And how do you classify marker-assisted selection? And let's just have a conversation around methods here. And I think this has as much to do with marketing and economics, Howdy, as it does with genetics. So if you want to take it first, go right ahead.
Okay. I was director of Harvest Plus for 15 years, and we had a choice to make. How much do we invest in transgenic methods, and how much do we invest in conventional breeding? I made the decision to invest in conventional breeding because even there were so many doubts about biofortification. Could we breed high-yielding varieties? Would they be nutritious enough to have a public health impact? Would Africans eat orange maize instead of white maize? If I added on top of that we were also using transgenics, there were just too many things to surmount. And when we went to Africa, we could say that we're only working on conventional breeding, and then that controversy was just put aside. Okay, now I'm no longer director of Harvest Plus. We've proven the breeding, we've proven the nutrition. We will prove that Africans will eat orange maize. We're in the process of doing that. I was co-author of a paper that was published last year that said now we need to move into the new techniques. We can't keep adding one nutrient at a time. We have to add several nutrients at the same time. And we also have to deal with climate change. So we have all sorts of things that we have to add simultaneously in the breeding process. And that's the only way we can get ahead of the game. And it's just the conventional breeding is just way too slow, especially given the resources that the public institutions have at their disposal to make progress. So I'm not speaking for Harvest Plus any longer, but I'm very, golden rice is going to have full approval for release in the Philippines in the next month or two. It's going to be followed up with transgenic iron and zinc. And we're going to have all three in rice. And I'm living in the Philippines, and I'm looking forward to doing whatever I can to advocate as rapid an uptake as I can of iron, zinc, and vitamin A rice in the Philippines. And once it works in the Philippines, it's going to spread around the world.
Thank you. Somebody pick up on that.
I would just say I really appreciate that optimism, and I think it's definitely important to be forward-facing. And I also am very optimistic. And when I think as scientists, we look more at what tools we can do to solve a particular problem. And most of us are in all of the above strategies. So, for example, how we use conventional approaches to develop these vitamin A enriched corn has been very, very successful, but that doesn't mean we want to discard tools for other problems. So I'll just mention that. And then also we have this really interesting parallel with the COVID vaccine. So if scientists had stuck with old techniques and not used biotechnology because of vague consumer fears and concerns, we wouldn't have these fantastic vaccines. And I think the difference maybe is that we see our friends and family getting sick, so we're willing to inject biotechnological products into our arm. But many people around the world don't see the struggle of farmers when their crops are susceptible to pest and disease, or when the children are malnourished. So I think it's a multi-pronged approach that scientists, of course, need to use the best techniques that are available to achieve their goals, but also to somehow make the rest of the world aware of the challenges faced by farmers.
Thanks, Pam.
Yeah, I want to go back to my talk. These are tools. We just need to make sure that we use the most efficient tools to solve the problems we have. Now, if we are in a situation where GMs are forbidden, so that's the scenario we have to deal with. But as a tool, we cannot neglect any tool to say this is A or B or C tool. If they are more efficient, if they get us to the goals we are setting for our programs, we should use them. And not be afraid of the market at the moment, because as Pam said, if you're afraid of the market or the signs the marketers send to us, we would stuck with the old tools long time ago. So we should be open to whatever tools that are there available to us and make the most efficient use of them. Regardless what kind of tool they are, if they're markers, GM, genetic engineering, whatever. So yeah, let's go use them as tools and not necessarily as the main goal of our programs. They're just tools. They should serve us.
I liked Pam's comment that scientists focus on tool development. And I think that there's this particular series, there's thousands of people that are watching these presentations, some live and some watching them subsequently after they're recorded. And I think that it takes a lot of clever scientists to come up with new tools and technologies to solve the problems that we're facing at any one time. And so on one hand, you have the science, and on the other, I liked Howie's comment that he was cognizant of the challenges. And on the backside of the tool development and technology development discussion, there is this commercialization piece that we need to be aware of and have open eyes and hopefully be good advocates for the value of the technologies that we're developing. As the technology developers, it's our responsibility to inform the public about safety, opportunity, and to try to have an open debate. And I think that that's the challenge for this particular group, and not just the panelists, but all the people watching these presentations as well.
And maybe a follow-up on that. A question came in: if we focus entirely on conventional breeding, are we likely to achieve the same advances that could be made if we were open to using GM technology or genome editing? Is this a price we pay or would we pay a price for broad market acceptance by avoiding the use of certain technologies? So that, I guess, is the same question that each of you were addressing, is just spun slightly differently. Would we be paying a price, and who would suffer, if we simply avoid the use of technologies that could get products into the market sooner? And is the price we pay for broad market acceptance in the immediate term, is there a second rollout later? And I think actually, Pam, your presentation sort of addressed that, because the fact that you cloned the gene had nothing to do with getting it out into farmers' fields. So the rollout into farmers' fields was entirely done by going back to a fairly traditional marker-assisted selection approach. And I think that was because you knew you wanted to get that to farmers as quickly as possible. Can you want to follow up on that? I mean, this is expediency, correct?
Sure. In the case of submergence tolerance rice, it was definitely expediency. It's very clear that if you have a marker-assisted bred variety of rice, there's no special regulation, so you can get it out in the field. And if it was genetically engineered, it would probably still be languishing. But there were some other aspects. I think isolating the gene was really important because we were able to isolate large chromosomal region, the whole chromosomal region, and so the team led by Dave McKill was able to develop markers from the clones that we had and introgress a very small region. And so the cloning was important for marker development. But then I'll also say, if you're putting a rice gene in a rice plant, there's usually, and Susan, you have a lot of insight into this, but usually there's not going to be a reason to use genetic engineering because you can use marker-assisted breeding. But in other cases, if you have a Bt gene from bacteria, you absolutely need to use genetic engineering. And so I think that's something that it's very subtle, but it's probably important for viewers to understand that there are times when marker-assisted breeding is not only going to be faster in terms of regulation, but it's also at the most efficient approach. And in other cases, think about fall armyworm marching through Africa. There are opportunities, for example, to introduce the Bt gene that may be an approach that is effective combined with other types of integrated pest management approaches.
And that's I think that was an important contribution, Pam, because it goes back to actually other points made by each of the other speakers. Tools, focus, and strategy. It's dependent on what the problem is, defining available opportunities to address it, and then a strategic rollout to help as many people as possible in the shortest time. I think every one of you is an exemplar scientist in this respect. I mean, we're lucky to have you dedicated to this field, and across the board, I think you all come from slightly different backgrounds working on different species. But there is an openness to try to use the appropriate tools at the appropriate time. Nobody is wed to the technology. So let me, maybe the last question for us all is just thinking about the need for more holistic approaches in terms of facing many of these multiple and complex problems. How are we going to train new scientists, engineers, and others in the future to be more systems-oriented and more multidisciplinary? We have educational systems that tend to specialize in a particular trait, a particular crop, or even a particular discipline. Do you see changes coming in how we prepare the next generation of scientists?
Maybe I can start. I think you have to give the scientists or the students a higher goal. In the sense that quote that I read at the end of my talk. You know, why do we have agriculture? Why do we have food? We have food for better health. And once that's your goal, you realize that the area that you specialize in is going to help attain that goal, but it isn't enough by itself. You have to understand how all the other components fit together. If your goal is to publish papers in your specialized area, then you don't have to understand how all the different things are connected together and how so interdependent we are. But so you have to give people a vision for a much higher goal and how your specialization fits into that.
We're running very short on time, so I don't know how much more time we have to answer. I think I'm being alerted here. I'm going to give some closing remarks now, and I have to cut the discussion off. Thank you so much to all of you. The second panel in this series will be entitled Genetic Innovations in Livestock and Fisheries, that will be held next Tuesday, May 18th at the same time. And we hope that all of you who are listening today will be able to join that session. As you heard from our speakers from our panel today on genetic innovations in plants, some of the genetic innovations being developed focus on specific traits, specific crop species, combinations of traits, and others focus on quantitative population improvement that targets overall crop performance in a given environment rather than improvement of particular traits. Still, other strategies seek to optimize the performance of diverse crops in rotation or as part of a multi-year cropping system. Taken together, it's clear that genetic innovations have a lot to contribute to crop resilience and enhancing sustainability of cropping systems, including the introduction of underutilized species. Many of today's innovations, which are discovered and applied in one crop species, also provide understanding that can accelerate genetic gains in other species with important knock-on effects. This is one of the most intriguing aspects of working in genetic improvement. We can begin to appreciate how similar the genetic building blocks are in many different species, despite their wonderful diversity. And with that, we'll close our panel for today. Thank you all. Thank you so much to the speakers and to those of you who submitted questions and to our participants near and far.